So if you remember, I asked you to note the fact that I am using a inner product there, right? Xi transpose x is just the inner product of two vectors, and the way I wrote the dual also I had only inner products in there, right. So in fact if I want to evaluate the dual, I need to only know the inner products of the two vectors. Likewise if I want to finally evaluate the use the classifier that I learned, I still need to only find inner products, right. So if I can come up with a way of efficiently computing these inner products, right, I can do something interesting. So what is that? So what do we normally do to make linear classifiers more powerful? Basis transformations. Somebody said basis transformations, right. So I can just take my h, right, replace it with some function h of x, right, that gives me a larger basis, right. It could be just replace it with the square, right. I take x and replace it with x squared, right, and then I will get a larger basis. And now it turns out that I can do a lot of math, but I can get a dual that looks like this. So that is the inner product notation, right. So if I can compute the inner product, so I can just solve the same kind of optimization problem, right, but I can do this in some other transform space, okay. So and likewise our f of x is going to be so essentially what I need to know is h of x for whatever pair x and x prime that I would like to consider, right. So in the training it is the pairs of training points, right, while I am actually using it, it is one of the support point and the input data that I am looking at, right. So at any point I just take these pairs of data points and I need to compute the inner product, right. So I am going to call this as some function, right, which is a kind of a distance function or a similarity measure between h of x and h of x prime, right. Such similarity measures are also called as kernels, right. So kernels are nothing but, so you might have heard of kernels in the context of support vector machines. If you have been trying to use libSVM or any of the other tools for some projects over the summer, you would have heard of kernels, right. Kernels are nothing but similarity functions, okay. So the nice thing about the kernels that we use, right, is that they actually operate on x and x prime, okay. They operate on x and x prime, but they are computing the inner product of h of x and h of x prime. Did you see that? They are going to work with x and x prime, right, but they will be computing the inner product of h of x and h of x prime. So I will give you an example. So the kernel function k should be symmetric, right, and positive semi-definite, okay. Positive definite, semi-definite is fine in some cases, positive definite. People remember what positive definite is, right? Right, and that if it is semi-definite, right. So essentially we want the quadratic forms to be, right, to be positive. Okay. We do not want to take x transpose Ax and suddenly find it is negative. So it's in fact, you remember I told you x transpose Ax is usually the quadratic form that we are trying, right, and that will actually mess us up big time in the computation. If the quadratic form becomes negative, okay, then we will have problems in all the optimization thing going through. Okay. So that's the mechanistic reason for wanting it to be positive semi-definite. There is a much more fundamental reason for it, which I have not developed the math or the intuition for you to understand. So it has to come at a later course. Okay. So hopefully in the kernel methods course, if you are taking it, you will figure out why that is needed. Okay. So there are many choices which you can use for the kernel. So something called the polynomial kernel, which is essentially 1 plus the inner product of x prime, the whole raised to the power d. So d is a parameter. You can have d of 2, 3, 4. You can even have d of 1, which is essentially your whatever we have solved so far, right? You could have d of 2, 3, 4, whatever. And the next one is called the Gaussian kernel or the RBF kernel, right? So where the distance is given by e power minus gamma x minus x prime squared, norm of x minus x prime squared. This is essentially the Gaussian without your without the normalizing factor, right? So that's why it's called the RBF kernel. So if you want to call it the Gaussian kernel, you actually have to make it Gaussian. Okay, it's otherwise called the RBF kernel. And then this is called the neural network kernel or the sigmoidal kernel sometimes. Not just the hyperbolic tangent, right? This is kappa 1 and kappa 2. Some constants, some arbitrary constants k1 and k2, which are your parameters that you tune, and this is x prime, the inner product. Okay. So these are some of the popular kernels which can be used for any generic data, but then depending on the kind of data that you are looking at, right, where the data comes from, people do develop specialized kernels. Right. For example, for string data, people have come up with a lot of kernels. When you want to compare strings, how do I look at similarity between strings? So the nice thing about whatever we have done so far is that you can apply this not just to data that comes from RP, right? So we have been assuming so far that your x comes from some p-dimensional real space, right? As long as you can define a proper kernel, right, you can apply this max margin classification that we have done to any kind of data. Doesn't have to come from a real valued space, okay, which is not true of many of the other things you have looked at, right? All those inherently depend on the fact that the data is real valued, right? Because of this nice what is called the kernel trick, right? So you could do all of these nice things. So as long as you can define appropriate kernel, right, you can actually apply this to any kind of data. So that's one very powerful idea. So just to convince you, so let's look at the polynomial kernel of degree 2, right? Operating on vectors of 2 dimension. Okay, so there are two 2's here. Okay, so the degree is 2, okay, the d is 2 and the p is also 2. Okay, but they need not necessarily be the same, right? I could have had a much larger thing, but it's easier for me to write. So this is what 1 plus I just squared it. Now if you think of a h which does the following. Right, so what is this function h? It's essentially the quadratic basis expansion, right? So I have two features x1, x2, right? So I give, so remember that x, right? Not confused. Okay, there you go. Right, x is x1, x2, right? They consist of two coordinates x1 and x2, right? So this is essentially the quadratic expansion. The first thing is 1, the second coordinate is x1, third coordinate is x2, so it keeps it as it is. Okay, then fourth coordinate is x1 squared, fifth coordinate is x2 squared, the sixth coordinate is x1, x2. Okay, it has done all the quadratic basis expansion, right? Now if I make this operate on x and x prime and take the inner product, so what will be the terms? 1, 2 x1, x1 prime, 2 x2, x2 prime, x1 squared, x2, x1 prime squared, right? x2, x2 prime the whole squared, and 2 x1, x1 prime, x2, x2 prime. That's exactly what we have here, right? So what is the nice thing about it is I can essentially compute the inner product of x and x prime first, add 1 and square it. So numerically what I will end up with is the same as what I would have ended up with if I had done the basis expansion, right, and then taken the inner product. That makes sense, right? If I had just taken whatever is the vectors, original vectors, let us say I have some 2, 3 and 4, 5. So instead of doing this basis expansion and then computing the inner product, right, I can just take the inner product right away, right? This is essentially 22 squared is the answer. So this, well, for degree 2 it might not seem great. What about degree 15 polynomial? I am essentially doing similar amounts of computation, except that I have to raise something to the power of 15, right? So any questions so far? Any questions so far? You're all good? Huh?
We are considering that we form a new basis with the first component being h.
Yeah, that is expansion. That is what basis expansion is. If you thought something else about basis expansion, please correct it. This is basis expansion, right? So I take the original data. Okay, I then essentially I said you could have a new components that are sin x, cos x. I mean, doesn't matter, right? You could think of variety of different ways of expanding the basis. In this case, I am just doing the quadratic basis expansion. Right? Is it clear to people? So whatever we have done so far, and so this whole idea of a kernel and other things are rather straightforward. So what I cannot write now for you is what is the basis expansion for the RBF kernel. It turns out that the computation it is doing is actually in an infinite dimensional vector space. Okay, so here the computation is in a 6-dimensional space. Right, I took some data point from a 2-dimensional space. Okay, I did computation in a 6-dimensional space, right, and I gave you back the answer, but all the time doing computation only in a 2-dimensional space, right? I only took the inner product of these two and then added 1 squared, so I am essentially doing computation only in R2, right, while the actual number I am returning to you is the result of computation done in R6. That is why it is called the kernel trick, right? So likewise, with the RBF kernel, I will do something in whatever is the original dimensional space you give me, but the resulting computation has an interpretation in some infinite dimensional vector space. Okay, so it's not even easy to write it down. Okay, so that's why the RBF kernels are considered pretty powerful. They work on a variety of data, right? but they are not all powerful though. Just have to be careful about it, right? So that is all there is to support vector machines. Okay, so we have done this support vector machines as well. So I don't know if people who have used lib-SVM or one such tool for that. For most RBF kernels, you would have tuned two parameters. One is C, which we already saw, right? That is essentially how much penalty you are giving to the thing. Other one you will tune is gamma, which is essentially this, right? It is some kind of a width parameter for your Gaussian. That is how wide your Gaussian is. It just controls that. So that is gamma. Okay. So those are the two parameters you tune, and for polynomial kernels you have a D and you have your C, right? And for sigmoidal kernels you have constants K1, K2, and you have C. And this form of defining a support vector machine is called as CSVM. Okay. There are other ways, other constraints that you can impose on it, not just the penalty on the Zeiss. You can impose penalty on the number of support vectors you consider, right? You want to say, so suppose I run the data and it comes back and says, okay, everything is a support vector, right? So that is not something interesting. How can everything be a support vector? Can all the data points be equal distance from the separating hyperplane? Not if you are considering linear, but when I am considering RBF kernels, right, the separating hyperplane can be very, very complex, right. So in which case you might end up with a lot of support vectors. Typically I do not know, if you have not thought too much about it and you are setting some very high values for C and trying to run this thing, you will end up with like 60% of your data as being support vectors. Okay. So instead of trying to do that empirically, saying that no, I only want 20 support vectors, so let me try different C, different gamma and so on and so forth, you can use something called the new SVM, new, not NEW, the Greek new, okay, new SVM, which gives you a upper bound on the number of support vectors that you are going to get. You will say, do the best you can, but don't give me more than 30 support vectors or something like that, to that effect. Okay.